Okay, what's happening, mathletes and Hazelwood? Mr. Nelson here for part 2 of, I don't know how many it's going to be in the end, but maybe this is the last one, we'll see, of exponent laws. And in the last video, we discussed kind of our 2 introductory exponent laws, which I don't even have a name for. The first was, we'll call it the fractional root law. No, that's not even right. Basically our radical exponent law, where a to the power of 1 divided by a number, a being any number, n being any number, can be rewritten as the nth root of that number a. And the second law we discussed in the last video was that a, any number, to a negative exponent n, is rewritten as the inverse of that positive root. So 1 over a to the n, which can also be written as 1 over a to a negative exponent, is the same as a to that positive exponent over an invisible 1, because it just flips to the other side of the divisor there. Okay, so now we're going to talk about a third law called the power of a power law. And this is these laws all complement each other and they work with each other to simplify, but this law tells us that a to the power of n, all to the power of m, is the same as a to the power of n times m. A power to a power, they multiply by each other. Okay? And this m will distribute to each variable, or each exponent of each variable, as long as those variables are being multiplied by each other. So what do I mean by that? If I have a squared b cubed to the power of 2, this 2 will come in here and multiply by this 2, and multiply by this 3. So we will end up with a to the power of 4, b to the power of 6. But I get ahead of myself. I will return to this idea right here. Let's just explore what this looks like in practice. So if I have x to the x squared to the power of 4, all this tells me is that I can rewrite this as x 2 times 4, which is equal to x to the power of 8. If I can use normal numbers. So 2 squared to the power of 2 can be written as 2 to the power of 4, 2 times 2. Okay? So exponents will multiply by each other if they're to each other's power. So if I have, so that's that. So returning to my previous thought, if I have variables multiplying by each other, like this, in a bracket, all to the same power, then this power will distribute and multiply by each individual variable's exponent. So this will be rewritten as x 3 times 4 is 12, y 4 times 4 is 16, z to the 4. This works, like I said, when these variables are multiplying each other. As soon as I toss in an addition sign to an expression like this, like x y plus z squared to the power of 3, for example, this can no longer just come in here and do that. The addition changes everything. So what I have to do is basically multiply this polynomial by itself 3 times. So this has to be written as x cubed y4 plus z squared times x cubed y4 plus z squared times x cubed y to the 4 plus z squared. And I would have to go through and do a whole bunch of stuff I haven't even taught you yet about multiplying polynomials and binomials. So all you need to know is you can only distribute this power law. This power law only applies when we're dealing with variables that are multiplying by each other. And there's no addition or subtraction in there to break it up. So, fairly straightforward law here. And now we can start kind of combining these 3 laws. before we move on to the product law and the quotient law, we can start combining these laws to simplify expressions. So what if I had something like the square root of x to the power 4? Well, how do I simplify this? Well, the first thing I'm going to do is realize, okay, I've got a root here. So I'm going to probably use my root law there. And x to the power 4 will become my a. So I can rewrite this as x to the power of 4 to the power of 1/2. Right? Because there's an invisible 2 here, which is my n. So I can write it like that. And then I can use my product of a product law to multiply these two together. So I get x to the power of 4 times 1/2, which, multiplying fractions, tells me that 4 can be written as 4 over 1, because 4 divided by 1 is 4, times 1/2. I multiply the numerator, I multiply the denominator, and I get x to the power of 4 over 2, which is x squared. Okay, if I had the cube root of x squared, y squared, well, in this case, this would be my a, and I would get x squared, y squared to the power of 1 over 3. And then, because these are multiplying, these two variables are multiplying by each other, I can distribute this into each of these, and I get x to the 2/3 times y to the 2/3, and that is my simplified expression. If I had, I'll leave this up for 2 more seconds. You got it, pause it, rewind it. So, if I had a to the negative 2 over b to the negative 3, all to the power of 2. Well, I've been saying that if they multiply by each other, this can distribute. Well, this can also distribute to division, okay? So I can actually say, okay, well, I can distribute this here, and I can distribute this here. So I would get a to the negative 2 times 2 is a to the negative 4, divided by negative 3 times 2 is b to the negative 6, and then these two numbers are very unhappy. They're not on the plate. They're not on the side of the divisor that they'd like to be. So I can bring b to the 6 up here. The 6 becomes positive, and the a jumps down below and becomes positive as well. And that's how we don't make exponents don't like to be negative. They like to do this. So if I had the fifth root of b to the negative 2, well, this would look like, this becomes my a now, so this would be b to the negative 2 to the power of 5, sorry, to the power of 1/5, 1 over that number, and then this would become b to the power of negative 2/5, and then this is negative, it doesn't want to be negative, so then this would become b1 over b to the power of 2 over 5. Okay? So we can also move in, so when we get these kind of strange fractional expressions, we can go from this back to here, but we have to know what's going on. So if I had c to the power of 3/4, and I said express as a radical. Well, this 4, because it's at the bottom, it tells me that I have a 4th root. I'm dealing with the 4th root. And this 3 tells me that it's c to the power of 3. So I could rewrite this. This is basically like, I know that I could write this as 3 times 1 over 4. And that's the same thing. 3/4 is the same as 3 times 1 over 4. So that's kind of the hint there. So this is the 4 is going to live here because that's my n, and then c will keep its 3 here. So this is the same expression here. So that is the power of power law. And I will do a video where we do a bunch of examples. I'm just not there yet, because there's a lot of different examples. They get more complicated. But for now, I just want to introduce the different laws. So let's just do the product law and the quotient law right now, because they're fairly straightforward as well. So this is the product law. So we have a to the n times a to the m. So a number to the power of n multiplied by that same number to a different power, or the same power, is equal to a to the power of n plus m. So we add those exponents. And we can only add exponents like this if we have two of the exact same number multiplying by each other, by itself. Multiplying itself. So if I have x squared times y times, actually I'll just do x squared times x to the power of 4, I can just write this as x to the power of 2 plus 4, or x to the power of 6. If I have x squared times y squared times x cubed, well, I look for the same variables here. I have two x's, so I would collect my x's. This is x2 plus 3 times y2, or x to the 5 y squared. If I had x to the negative 1 y squared, I'm going to use different letters just for fun. If I had e to the negative 2 times d squared times f to the 1 times e cubed times f squared, well, what would I do? I would collect. So first I would find, okay, I've got two sets of e's and I got two sets of f's. So I got e here, e there, and I've got f here, f there. So then this would work out to, I collect my e's, I say, okay, I've got e negative 2 plus 3, I've got d squared, and then I've got f1 plus 2. This works out to e to the 1 d squared f cubed, or ed squared f cubed. I don't have to show a 1 exponent, because e to the 1 is just e. Okay? If this worked out that I had a negative d here, well then I would use my law right here and say, okay, I'm going to rewrite this as e f squared over d squared. There's no addition in here, so they can just jump around this line as they please. The invisible divided by 1 there. Okay, so that's the product law, and then its sister brother is the quotient law. So a to the n divided by a to the m is equal to a n minus m. So this can be written as a to the n divided by a to the m. We can show division two different ways. A to the n minus m. So all that means is that if I have a variable showing up on both sides of the divisor there, so if I have, say I had x squared y cubed over, well, let's start simple. If I have x squared divided by x to the 3, I can rewrite this as x to the power of whatever's on top 2 minus 3 is equal to x to the negative 1, which I would then write as 1 over x to the invisible 1, which we don't need to show. So if I had x cubed, y to the negative 2 over x to the negative 1, y to the 1, 8x to the negative 2, y to the power of 2. And I said simplify this. Well, you'd say, okay, well, I've got x 3 minus whatever's on the bottom, divided 3 minus negative 2, times y, negative 2 minus 2. And this would give me x 3 minus negative 2 is 3 plus 2, so x to the 5, y to the negative 4. And then this exponent is unhappy, so it's going to want to jump to the bottom. I get x to the 5 divided by y to the 4. And that's how I would show my simplified version of that. Isn't that neat? We get from here to this. I think it's pretty cool. It's like magic. So these are the laws, and from here, things start to get, starts to get kind of fun. So I'll just give you an example of the type of problem that you might start seeing, where you're going to have to employ all these laws. And yeah, it's going to be hard at first. You're not going to know where to start, but you're going to practice. You're going to make mistakes. You're going to fail forward. You're going to talk to Mr. Nelson when you have problems, either in person, if you're in my class, or if you're somewhere around the globe, you're just going to comment me and I'll try and help you. But yeah, that's what we're going to do. So it's going to be, so say I give you something like, what's a good one here? Right there. So say I had something like a to the negative 7, b to the power of 7, over a to the negative 9, b to the power of 10, to the power of negative 5. Okay, and I say simplify this. Well, I can start in different places. It doesn't actually really matter where I start. Okay, so I could start with my power of power laws and distribute this 5 to each of these numbers in here, because there's no addition, it's just multiplication and division. I can actually distribute this 5 to each number here. Or I could start by doing using my quotient law and just getting down to 1a with one exponent and 1b with one exponent. I could also start by moving my unhappy negative exponents to the other side of the divisor there. So in this case, I am choosing to, I just want to collect all my a's. I don't want to have 2 sets of a's and 2 sets of b's. I just want 1 set. So I'm going to start working on the inside here. So I'm going to get, well, I know that I'm going to have a to the negative 7 minus negative 9 times b to the power 7 minus 10, all to the power of negative 5. And then that becomes a negative 7 minus negative 9 is a squared times b to the negative 3 to the negative 5. Now I could take this b could take a hike and go below, go to the basement here, below the a, but first I'm going to distribute out this negative 5, which I can do because there's no addition or subtraction happening here. That would force me to multiply the polynomial by the polynomial. So then this becomes 2 times negative 5 is negative 10, and then negative 3 times negative 5 is 15, positive 15. Now I'm almost there. I just have one unhappy exponent here. So he's going to drop down to the basement, to a safe place, and I get that. And this is my finished, look at, I got all the way from this complicated thing right down to there. Isn't that just beautiful? Beautiful. So that's that. So I think that's enough for today. I've introduced some beautiful laws. There may be more I'll introduce as well as I see fit, but I think for now this is enough to keep us moving ahead in this part of the course. So thank you for watching. Bye.